Welcome to Lecture 13. We're going to continue with double replacement reactions for the first part of the lecture, and then we're going to move into every chemistry student's favorite topic, and that is stoichiometry, this weird word right here. Okay. What we're going to talk about today is a different kind, well, still a double replacement reaction, but the driving force for this reaction is a little different from the precipitation reaction. So in review, we took aqueous ionic compounds, two of them. Here's a classic example. And we switched partners. Sodium, the positive from this one, goes with the negative from this one. So double date, switch dates. Sodium nitrate, if we consult our solubility rules, is aqueous. But silver in combination with chlorine, which is the other possible new product, is not soluble. So it precipitates. When these four ions are in solution and silver and chlorine come up against one another, they're not very soluble, so they form a solid. Essentially taking products out drives the reaction forward. And when you get into 132, you'll learn that not all chemical reactions just go in the forward direction. Well, for double replacement reactions, there are three things that drive the reaction forward. One is the formation of a precipitate, as we talked about last time. The other is the formation of a molecular compound like water or CO2 that is going to stay together. The gas, if you form a gas, that's the third type. So if you form a gas like carbon dioxide, that leaves, it's a gas, so it leaves the reaction mixture unless you have it closed off. And that, taking a product out, drives it forward. Forming a molecular substance like water essentially takes the ions that participated in making the water out of the mixture, and therefore that tends to drive the reaction forward as well. So we're going to be looking at acids and bases today. Most of the time, if those acids and bases were aqueous to begin with, just like we've been talking about with our previous kinds of reactions, they're going to form water and a salt. So when you take an aqueous acid and an aqueous base and mix them together, you are going to form a water and a salt. Now remember, in the last lecture I said that chemists call pretty much all ionic compounds salts. Okay, acid-base reactions are also double replacement reactions. Instead of forming a gas or a solid that pushes the reaction to completion, we form water. Water has a very low tendency to fall apart, again, to produce hydronium and hydroxide. We will investigate this in exam 4 material when we look more at the chemistry of water. Salt and water. Okay, so here is a example right here. We've got hydrochloric acid, which is aqueous, and sodium hydroxide, which is dissolved in water as well. So it's still double date, switch dates. The positive from this one goes with the negative from that one, and this is what produces the water, the H from the acid and the OH from the base. What's left behind is the other possible combination. Most of the time it's a soluble salt, as in this case, sodium chloride. So a salt and water, double replacement reaction. We're going to practice our net ionic equation writing abilities today, a little bit more, and so on. So this is just a little continuation on from what we did last time. Let's write the complete ionic equation for this equation here so that I can show you that you indeed arrive at this net ionic equation. So we have not, I skipped the complete ionic equation. Let me give myself a little room. So I'm going to be separating the aqueous things into their ions, okay, and cancel out the spectators. So H plus Cl minus splits up this strong acid. Sodium hydroxide, strong base, but also an ionic compound, splits up into those two ions. The OH comes together with the H plus to form water, and we leave that together because it's a molecular compound. And sodium chloride, which is aqueous, but we're going to write it in its ionic form. Okay, spectator ions are the chlorines and the sodiums. Most neutralization reactions, you end up with essentially this same net ionic equation. One exception, and we looked at this example at the end of lecture 12, and that is if you have a carbonate in the presence of an acid, you produce CO2 and water. So this is the net ionic equation that I showed you at the end of lecture 11. Let me give myself a little room and we will write the complete equation to remind you of where this came from. So calcium carbonate not be written any other way since it's a solid. H plus probably came from an acid like HCl, which was dissolved in water. And we produced calcium chloride, aqueous, plus the H2CO3, the carbonic acid, which doesn't exist really, and so we rewrite it as carbon dioxide and water. Now what I did not show you was how that works. Okay, so here's the formula for carbonic acid, which is what you would get if you took the positive from the acid and with the negative from the calcium carbonate. CO2, take CO2 out of this and you're left with H2O, so that's how you get CO2 and water. Alright, so if we wrote that in an ionic form, we'd have 2H pluses plus 2 Cl minuses. Can't rewrite that. Calcium plus 2 Cl minuses. And I can't rewrite either carbon dioxide or water, so the only thing that canceled were the chlorines. And that's how we end up with this net ionic equation. Okay? All right, let's do some practice because this really is nothing new. It's just some different examples. Okay? All right, so we've got a beaker of nitric acid is neutralized with calcium hydroxide. Write a balanced molecular and a net ionic equation for this reaction. Probably need to write the complete ionic as well. So nitric acid, this is one of the strong acids you need to memorize, dissolved in water, plus calcium hydroxide. Calcium has a +2, hydroxide has a -1. So I need 2 of those -1s to cancel out. And this is aqueous. Positives and negatives combine to produce water, my molecular substance, and calcium nitrate. Calcium is +2, nitrate is -1. So I need 2 of those -1s, and that is a soluble compound in water, so aqueous. Writing in its complete ionic form. Let me balance. Need 2 of these. So 2 H's and 2 OH's produce 2 waters. That's the best way of looking at these. Look at how many hydrogens and how many OH's, and you should have the same for both, and that's how many waters you're going to produce. Okay, so 2H plus 2 NO3 minus, distributing that 2, plus calcium with a +2, and then parentheses, bring that subscript to the front. Don't do anything to the water. It's molecular. Plus the calcium, and the 2 comes in front, 2 nitrates. All right? Spectators, nitrate, and calcium. So you end up with 2H plus 2OH minus, gives you 2 waters, and if you take that to its simplest form, we end up with that net ionic equation that most acid-base neutralizations provide. Okay, I'm going to scroll. Oops. All right, I think we have one more. Yes, we do. Whoa, need some room here. One more example before we get into stoichiometry. Okay, there we go. All right. Oops. Need to be able to read the question. All right, a beaker of sulfuric acid. So let's just go ahead and write that formula. Another strong acid you should know. So that's aqueous. Is neutralized with potassium hydroxide. It's a little unfortunate that we use the term neutralize. You don't always end up with a neutral solution, as you will learn in Chem 132. All right, so writing our products, H's go with the OH's to produce waters. Notice I have two hydrogens here. I'm going to end up needing two hydroxides, so I will be making two waters. And it's the formula of the salt that's going to help us with that. K has potassium has a +1 charge, sulfate has a -2. So I need two of those K's to balance out the potassium sulfate, and this is aqueous. Potassium's group 1, so I did indeed need two of those. Writing the complete ionic reaction, 2H plus, the 2 comes in front, sulfate with a -2 charge. Distribute the 2 here. Leave the water alone. Bring the 2 in front, 2K plus SO4 with a -2 charge. Your sulfates and your potassiums are spectators, so we end up once again with our acid-base net ionic equation, and I can rewrite that in a simpler form by dividing all of the coefficients by 2. All right, so really it's just one more example of double replacement reactions. All right, one thing you might want to find, pause the video and go find, is your mole chart from Exam 1 material. It is coming back today. Calculator's back as well. All right, we are going to be looking at a subject that is not as hard as perhaps your high school teacher made it. It's really quite simple if you follow the steps I've laid out here and you're organized about how you work the problem. Stoichion is from the Greek meaning element, and metron is to measure. So we are measuring. In fact, this is a lot like cooking, stoichiometry. It's about proportions. So if you double a recipe or cut it in half, that sort of thing. One thing that we have to, we've been working with chemical equations in the last 3 lectures, and the coefficients that are in front of the species, the chemical formulas, can be interpreted as what we've been using them as particles. So this 2 in front of this H plus, the 2 in front of the H, why it does that sometimes. I'll just start over. Okay, so if I write 2H plus 2OH minus goes to 2 waters, even though that's overbalanced, we'll just leave it alone. This 2, we've been essentially meaning it's particles. When you did the Chem Balancer program, you counted symbols. These symbols are a representation of an atom. So we've been treating these particles, these coefficients, as meaning particles as we've learned to balance chemical equations and so on. Well, just like we were able to make a connection between particles and the mole The mole is just a counting unit. So if I have a 2 in front of H2O, it means that I have a total of 4 hydrogens. But that 2 can also be interpreted as a mole. So I'm just changing the counting unit, and we did that when we studied the mole chart at the beginning. This 2 can mean I have 2 water molecules, or it can mean I have 2 moles of water. And if I have 2 moles of water, I have 2 moles of water, I have 4 moles of hydrogen if I took it all apart, and 2 moles of oxygen. Okay, same thing here. 2 moles of hydroxide means I have 2 moles of oxygen and 2 moles of hydrogen. Okay, so the coefficients in these chemical reactions can mean both particles and moles. All right, so that's the first thing to realize. And we're ready to get started. So here are my steps for stoichiometry. It's only 4 steps, and there's a 2B. You won't use that till the next lecture. But the first 4 steps we're going to use today. So you're going to start out a stoichiometry problem always with the balanced chemical equation. And because these coefficients, as I just mentioned just now, mean both particles and moles, I am going to use the mole, of course, as my central counting unit. So if any amount that's given to you in the problem needs to be converted into moles. So I always tell students, if you're not in moles, get there. So you may be starting off with 20 grams, or you may be starting off with, later on we'll do other amounts with different conversions. But if you're in grams, then convert to moles. And that's why I needed you to get your mole chart out, because we're going to need to remember how to do that. You need your periodic table in front of you. Won't be using Avogadro's number so much because this is a more practical conversion from grams to moles. This is the new step, okay? What I've just talked about here, we've learned how to balance chemical equations. We know how to go back and forth between moles and other things, but so that's nothing new. But this is the new step, step 3. Use the coefficients in the chemical reaction to obtain a mole ratio, and we are going to do it as 2 over from. Or another way to look at it as question mark, what you're being asked about, over what you were given. So either way, they are equivalent, and that is what we're going to do to compare one thing to another in a chemical equation. Then, if you need to change back out of moles, that's nothing new either. All right, so let's go ahead and get started by doing some examples. So we need to learn how to do that mole ratio. All right, so I have a chemical equation right here. The question is, for the reaction shown, calculate how many moles of ammonia form. So I am going to start off, I want to scroll before I write, when each amount of reactant completely reacts. Looks like I got that twice, so let me get rid of that. All right, maybe we can even get that equation up closer to the question. Nope. All right. So so we want to know moles of ammonia, okay? So the first thing I'm going to do is make sure my equation is balanced, and I am going to write under ammonia what I'm being asked. So this is my question mark. I want to know how many moles, okay? I am going to give myself a little room right here. And I didn't need as much here. Okay. All right, so question mark moles. So my first amount is 5.3 moles of N2H4. So I am given the amount of one other substance. Now it does not matter where you're given, it doesn't matter what side you're on, what direction you go in, nothing matters. So this is the deal. If I know the amount of one substance, doesn't matter where it is in this reaction, I can get the other substances using this mole ratio. So I'm already in moles, I have a balanced chemical equation, so I'm ready to move. This is a horizontal step. I tell students, and as we get into the full-fledged where we're using all 4 steps, it's like a box. So you're going from what you're given to moles if you needed to change, then you move to what you're being asked about, and then you go back to whatever amount they are asking. So if you can keep it straight, keep it organized, this is really not that difficult. All right, but so I only have to do one step here. I'm not doing the whole box. I'm only doing the mole to mole step, which is using the mole ratio, the new step. So it is the coefficient. I'm going to take this amount in moles that I was either given or I got there, and I'm going to multiply by the coefficient of what I'm moving to, TO, or where the question mark is, over what I'm coming from, or from what I was given. So 5.3 times 4/3 is going to give me my new amount. And I can compare any two this way. And we're going to do this 4 times. Let me get my calculator. All right, so probably already got yours already figured out. I wasn't ready. All right, so 5.3 times 4 divided by 3. Okay, so I get 7.07 as my, now I'm given 2 significant figures, so we're going to round that to 7.1 moles. Okay, so my very first answer is 7.1 moles of ammonia. All right. All we're going to do for B is change the amount of what we started with, and we're still in moles, 2.28 moles of the N2H4. I'm going to use the same mole ratio, 4/3, because I'm going between the same two things. And I get 3.04 moles for B. Or for 2 significant figures, I guess I had 3 given to me in B, so I can leave that as 3.04 moles. The coefficient of what you're moving to, which is right here, over what you're coming from, which is right here. Okay? In C and D, we are going to be going from nitrogen to ammonia. Okay? So things are going to be a little different. So I'm going to go ahead and erase what is here. Use a slightly smaller eraser. And I'm going to set up my new scenario. Now, with you and paper, that you're actually doing this on paper, you might want to even write your chemical equation again so that you can keep everything organized, so that I can put the amount given under the substance I'm being given, and then I can write my question under the substance I'm being asked about. Now, this is one thing I want you to remember. We are not changing the master recipe, okay? Just because I've changed the amounts. I don't change the coefficients. I've seen students do that. So I'm already in moles, so I need to move to my question mark, which means I will be taking those moles and multiplying by the coefficient in front of the thing I'm moving to, or for the question mark, over what I'm coming from, which in this case is the nitrogen, and it has a 1 in front of it. So 5.8 times 10 to the minus 2. I got 0.232 moles for my answer to C. Two significant figures, so we'll leave it as 0.23 moles of ammonia. All right, same thing in D, 7.76 times 10 to the 7th looks like moles of nitrogen, and I'm going to move to the same, so I've got the same mole ratio going on here, so times 4 over 1, and I'm going to have to get a different calculator. I was using my phone. All right, so 7.76 times 10 to the 7th. That's a lot of, divided by, I'm sorry, times 4. And I get 3.1, 3.10 times 10 to the 8th is what I got for D. And I can take it out, 3.10 times 10 to the 8th. I'm going to check that one more time. Yep, that's what I got. So 3.10 times 10 to the 8th moles. Remember, now that we've gotten back to using the calculator again, never write a number down without putting the unit after it, especially when you're doing these kinds of calculations, because your attention gets diverted and you look back at the number you wrote down and you really have no idea what it's for. And another reason to keep it neatly organized in terms of your information as it relates to the chemical equation is you know where you are. All right? All right, so that's the new step, the mole to mole step. All right, for the reaction shown, calculate how many moles of each product form when the given amount of each reactant completely reacts. And then they have this statement of assume there's more than enough of the other reactant, so don't worry about that. Has to do with limiting reactants, and we'll deal with that in the next lecture. All right, so A, for how many moles of each product is my question. So let me go ahead and put that in. So question mark moles, question mark moles. All right. I am going to start with in A with 4.6 moles of the C3H8. All right. So I am going to 4.6, right? I'm already in moles. I have a balanced chemical equation. So I'm ready to move to my first question mark. So this time it'll be times what I'm moving to, which is 3, over what I'm coming from, which is 1. So 4.6 times 3. Change calculators. I hate that calculator. 4.6 times 3, and I end up with 13.8 moles for my first product. Now, in order to answer this second question for the water, I can either come back to the C3H8 and do all the way across, or I can go right from the CO2. I will get the same answer no matter which one I use, and I will prove that to you. So I'm going to go back to the C3H8 and use my 4.6 moles, and then move to the water. So it'll be times 4 over 1, okay? So 4.6 times 4, I get 18.4. 18.4 moles, all right, of water. But if I went from the CO2, I would take my 13.8 times 4 over 3, and I get 18.4. So it doesn't matter. That's the beauty of stoichiometry. These coefficients are giving you the proportions related to one another. So I can use any two. I can go in any direction. It doesn't matter. Okay? That is A. Now let's do B. I have to erase. Okay, and this time I'm going from oxygen, so 4.6 moles of oxygen. Okay, how many moles of each product? So in these first two examples, we are really honing in on that new step, the mole to mole step, the mole ratio, using the mole ratio. This is the only step in which you use the coefficients. All right, so I'm going to take my moles, I'm already in moles, and I'm going to use my coefficients times 3/5. I am moving 2 carbon dioxide from oxygen. So 4.6 times 3 divided by 5, and I end up with 2.76 moles of CO2. Okay, I'm just going to go right next door because it's easier, times 4/3. And the best thing to do when you're doing these stoichiometry problems is just don't clear your calculator, because chances are the next number you're going to be working with is the one you just finished getting in your calculator. All right, so there are my moles of CO2 and my moles of water. In this second, to get the water, I was moving from the CO2, so that's why its coefficient is on the bottom. I was moving to the water, and that's why its coefficient is on the top, 2/from. All right, I'm going to erase and do C. All right, so we're going back to the C3H8, and we're going to put in a different amount this time. 10 to the minus 2 moles. Question is still the same. Okay, so I'm already a mole, so I can move, times 3/1 for the carbon dioxide. And I get 0.167 for the carbon dioxide moles. And then times 4/3 to get the water. And I get 0.223 moles. Right? And that is C. We're going to use exactly the same number of moles of oxygen in our last step. Okay? All right, so one more time. 5.58 times 10 to the minus 2 moles of oxygen. We're going to move to CO2 and water again, times 3/5, because I'm moving to the carbon dioxide from the oxygen. .033, 0.033, or 3.3 times 10 to the minus 2. It's actually 335. So if I do put it in scientific notation, I can get a little more accuracy out of it, as I can use 3 significant figures. So that many moles of carbon dioxide, and then moving to the water, see that number is in my calculator, times 4/3 to go to the water, going to water, so that's why the 4 is on top, coming from the carbon dioxide, that's why the 3 is on the bottom. So times 4 divided by 3, and I end up with 4.46 times 10 to the minus 2 moles of water. And that is 2 multi-step multi-part problems where we are honing in on that new step, which makes it stoichiometry. All right, let's see. All right, we've got two more, and we're going to probably do a little bit more on these two rather than just that one step. First of all, in number 3, we've got to balance this equation. All right, so at any time, stop the video and give this a try on your own. So we're going to put a 2 there for the aluminum. 3 sulfates. I need a 3 here and a 3 here. Okay. What kind of reaction is this? This is a single replacement reaction, and we will be honing in on those in the exam 4 material, actually. You can write ionic equations for these as well, but everything won't cancel because aluminum is a solid here and it's a 3 plus over here, so remember that. All right, we've balanced our equations. How many moles of sulfuric acid, so before I go any further, I'm going to write down my question, are required to completely react with 8.9 grams of aluminum? All right, so you see that the two things we're working with are on the same side. That's okay. All right, I have a balanced chemical equation. I've written down my info. If you're not in moles, get there, and I'm not in moles, so I am going to do what I call a vertical step in this box, okay? And I know how to go from grams to moles. I know I need a periodic table. All right, so I am going to grab mine, and I'm going to ask you to try to remember how you go between grams and moles. Get your mole charts out. All right, I've got my periodic table. Now, when I'm doing stoichiometry problems, I like to write my molar masses, and that's what I'm going to be needing, above the species that I'm working with. That way, if I need to go back and redo anything, I don't have to look it up again. Okay, so aluminum is 26.98. Now, when you're doing this mole of grams to moles step, we're not using the coefficients. We didn't use them before when we first learned how to do this, and the only time we use the coefficients is when we're moving. So I'm going to write it right here. I'm going to take 8.9 grams of aluminum, and I'm going to remember with my units that I need to divide by the molar mass in order to get those grams to cancel out. So 8.9 divided by the 26.98. And I end up with 0.33 moles. Now, you can write that down on your paper, but I'm leaving in my calculator 0.32987. I'm not clearing it, okay, so I won't lose any accuracy. Now I have my moles. I can move to my question mark by multiplying times the mole ratio of what I'm moving to over what I'm coming from. So that number's right there in my calculator, times 3 divided by 2, and my answer is 0.495, which is a few too many significant figures, so we'll call it 0.50 moles. Okay, so that was moles. When I move using the coefficients, I am still in moles. All right? And that is B. C, how many grams of hydrogen are formed by the complete reaction of 0.341 moles of aluminum? I have a new scenario. This is common with stoichiometry problems. So I really need to erase what I have so that I can put my new information underneath. Okay? All right, so I've already put my question mark, and I'm starting with 0.341 moles of aluminum. Now, in the previous problem, I had to get into moles, I moved, and then I stopped. So I did this much of the box. We're doing half a box still in this one because I am already in moles, so I'm going to be able to move, and then I'm going to convert back to grams. Okay, so I'm in moles, So now I can move to my question, times 3, the what I'm moving to over what I'm coming from. So 0.341 times 3 divided by 2, and I get 0.512 moles, 0.512 moles. So you're not quite finished yet. 2 H's, if I take the molar mass on the periodic table and multiply times 2, because of the little 2, I get 2.016. So 2.016 or 2.02 is the molar mass times 2.016 grams per mole, and the moles cancel. Times 0.512, and my answer is 1.03 grams when I multiply these two. So let me make that clearer by erasing some of this, and that is equal to 1.03 grams. Now, what I'd like to show you before I move to the next problem, because we're doing pretty well with time, I would like to show you how in this last example, how we could have done that all in one conversion, not a conversion step, but using dimensional analysis, I can do the same thing I've just shown you. Now, I like the visual of the box, but let me show you what I'm talking about. Okay, I'm starting with 0.341 moles of aluminum. All right, I need to get to moles of hydrogen. There are, oops, erased my balancing too. Let's see, there's a 2 here, there was a 3 here, and there was a 3 here. 6, yes. Okay, so times. So I'm in moles of aluminum, I need to get to moles of hydrogen. So there are 3 moles of hydrogen. What I want on top for every 2 moles of aluminum. And that cancels. And then I want to get to grams of hydrogen, so I use that molar mass, the 2.016 grams per mole of hydrogen. And then it tells me what to do. So 0.341 times 3 divided by 2 times that to get our final answer, which was 1.03 grams. All right, so get into moles, move using the coefficients. The other conversions are the mole chart. Okay, scrolling to our last problem here, and it's a multi-step problem, so oops, wait, there we go. All right, so I've got an equation here. Is it balanced? Looks like it is. What minimum mass of hydrochloric acid in grams would dissolve a 2.8 gram iron bar on a padlock? So I am doing the whole box because I am not into moles, so I am going to have to get there, and then I will move, and then I have to convert back to grams. All right, so I will do that up here, and then we'll show you how to do it with dimensional analysis. Now I am going to need the molar mass of both of these substances, so I'm going to go ahead and write those above each, so that makes it nice and easy. All right, I am going to need those. In my first step, I'm going to be converting to moles of iron because that's what I'm giving. You always start with the number you're given. So 2.8, so I'm going to do that down here as well. So 2.8 grams of iron times 1 mole of iron has 55.85 grams. Okay, so that is my first step. So if I do that and stop, I end up with 0.05 moles. Okay, so now I am in moles, I got there, and now I can move by using the mole ratio of what I'm moving to over what I'm coming from, that has a 1 in front of it. Okay. And I get 0.1 moles. So dimensional analysis, this is what I'm doing. I am in moles of iron at the moment, but I want moles of HCl, so that goes on top. 2 moles of HCl for every 1 mole of iron. And I am officially out of iron. I've moved away from iron, just like my diagram up here shows, because now I am under the HCl. But I want grams of HCl, so I have one more step, and that is to multiply by the molar mass, which is always in the units of grams per mole, and the moles cancel, and I will end up with my grams. So times 36.46, 0.1 times 36.46, so I should end up with 3.65 grams as my final answer. Okay, it's really quite simple. Balanced chemical equation. Write the info you are given in the problem under those species. Get into moles. Move using the mole ratio of 2 over from. That is the only time you use the coefficients. Only step for coefficients. Okay, then I will convert back to whatever I'm being asked for out of moles. Sometimes you stop at moles. All right, let's see if there's any more to this. How much hydrogen would be produced by the complete reaction of the iron bar? So how much usually means grams, so I'm just going to put that in. And luckily I still have, it was 0.1 moles of this, and it was 0.05 moles of this. So I can use either one. I have to go back to moles in order to move over to the hydrogen. So I'm just going to go ahead and use the HCl. That's okay, won't make any difference. Hydrogen has a 1 in front of it, the thing I'm moving to. HCl, what I'm coming from, has a 2. So I end up with 0.05 moles of hydrogen. But look, hydrogen and iron have the same coefficient, so they're going to have the same moles. And then all I have to do is convert back to grams. The molar mass here is 2.016. So times 2.016 grams per mole. And I get 0.1008. And my significant figures is really 2. So I guess it's 0.1 grams. 0.10. Right? And that is stoichiometry. We will certainly practice more in class, on sapling and in class for recitation. So not so bad.